So it is time, and good afternoon, class. This is the online SAR course supported by TSU, Taiwan Space Union. Today, we invite Dr. Chih-Heng Lu to deliver a SAR topic. The title is the Introduction of SAR interferometry, which is important and fundamental the SAR topic. The Dr. Lu received his PhD degree from Graduate Institute of Applied Geology, National Central University, Taiwan in 2018, and currently he is a research in Research Center for Environmental Changes in Academia Sinica. He is a young and active researcher about in the field of the SAR in Taiwan, and his research is about monitor the surface deformation, migration, and variation in different spatial temporal scale with geology and geodetic and remote sensing data. Okay, let's welcome Dr. Lu. The stage is yours.
Okay. Thank you, Professor Lin's introduction. I'm so glad I can enjoy the TSU's SAR course. Okay, so first I will share my PowerPoint. So it's my pleasure to join the TSU SOS SAR course. Yes, I've just got my PhD, just like introduced from Professor Lin. I'm very interested about SAR's process, especially in interferometries, because we're very interested about surface deformation, just like the earthquake or land subsidence. So in today's course, I will provide 3 sessions. First is what is SAR interferometry, and the second is the processing of the SAR interferometry, and the third is the limitation and the error source. Okay, so I believe based on everybody's, you already learn a lot of the information and the knowledge about the SAR. So here I just introduce and I just explain what is the interferometry. This idea is based on the light. So in these figures, you will found here the box means the coherent light source. It means in this box you will always put the light source from here. And here is an interesting equipment. It is a half silver mirror. It means when the light crosses these mirrors, some part of light will cross them to another side, and some part of light will reflect to another side. Okay, to another side. So when the light crosses these mirrors, it will go to the right side mirror or the top side mirror. When the right side mirror reflects the light to the half silver mirrors, some light will penetrate back to the original light source, and some signal will go to the detector here. And then if we found if it is the top side of the mirror, the signal still will reflect from here, and then penetrate here. Some signal will cross here, and some signal will reflect to another side, go back to the light source. So if very ideal situations, we will seek the top side of the mirrors signal will get from the detector is like here, and the right side of the mirrors, the reflect signal will detect here from the detectors. If their frequency and their wavelength and layers come from the same sources, we can stack them and enhance the wave. The signal wave is become 2 times of the original. But sometimes if we change the situations, we just put the right mirrors a little bit far away from the half silver mirror. It's like the distance is extends distance. You have found the mirror, the signal from the right mirrors. The arrive time and is a little bit different about the top mirror signals. And when we stack these 2 signals, you will find the signal is the amplitude is decreased, and the signal is not strong as the before because they are not because they are not almost the same as the same frequency at the same times. So this will tell us the strong is the situation is changed. So if we can put this like the GIF figures, you will find okay when they are almost the same, the amplitude will increase. When they are the shift almost the one single wave, the signal will almost reduce near reach the 0. So what is importance for these informations? It will cause, you say the right side. Here is a dark line, bright line, dark line, bright line is reflect this total stacking results. So it will dark light, dark light. This behavior is like interferometry, and then it will help us know some information about, like a preview. I say I just move some distance from the right side of the mirrors. So this interferometry will give me the information. Something situation change. For our case, is the distance change. But it have some necessary condition for the light. First, you need have the same path direction for both light. For the mirror, the center of the silver mirror, you have found every light will come from the silver mirror. So the detector will get the same path from the signal mirror. If we change the silver mirrors, it means the path will something change. So that will make us hard to become interferometry signal. And the second is about the same frequency. Yeah, because if we change the frequency, it's hard to stake this signal. And then the third is we should have the stable phase, because if the wavelength is changed, it's really hard to get together at the same frequency and the same arrive time to make the interferometry. So when we have the idea about light, so we can use like the fringe, the right side like the fringe, to analyze the relative relationship between 2 phases of the both lights. So if we can use the same ideas into the radar signal, is any possible help us to know how to difference the surface deformation if different 2 times and or more time or a multi-temporal situation. So we will try to put some information into the interferometry. But as you already know, the SAR image contains 2 most components. Yeah, this is a complex SAR image where including intensity image and the phase image. And in this course, we will focus on the face image. Yeah, we just use the face because the face can support us some information about the distance change, or we say just like we interested about the surface deformation. The first apply the surface deformations we call SAR interferometry, and as known as maybe you will know the InSAR is almost the same mean, and then you will first to measure the topic is the topography, or you will say the elevations. So this is a case use the airborne SAR. It means we set up two SAR sensors on an airplane, and when he flies through the interest areas, the two sensors will get the signal, and then the signal is from the airplane, so it will put the signal and get the reflect signal in the airplane. So when we put these two signal to do the interferometry, just like before I say, like the light, the algorithms, that we can get the phase difference. Like the left side is radar interferometry. It like become a fringe. And here is from the 0 to 2 pi. Is pi is 3.14 and so on. And when we got this, and we want to become the numbers, we will unwrap that, and then we can get the right side of the result. Here is show the meters difference. Yeah, and this case is in the San Francisco. So here the very straight, linear ground truth is the Golden Gate. It's in the San Francisco Bay. Yeah, he's here. But when the scientists got the quite good result in the airborne systems, they start to think about how about we can get the whole Earth topography. So they start to develop a mission. It's called a Shuttle Radar Topography Mission. It's SRTM. I believe most people you already use this data. We often call we usually call it the SRTM DEM, and it maybe have the 30-meter resolution. Yeah, some place maybe supports a 19-meter resolution, but it almost supports us all of the Earth, but there's some limitation. If the area is higher than 60 degrees in the north, or lower than negative 60 degrees in the south, it can support your DEM data. You may need change to search like ASTER or others DEM data to get the two porous areas. But in most places, this is quite good for us use. And how is to get this DEMs is they launch a shuttle, and then in this shuttle, including two C-band antenna and the two X-band antenna, and the one antenna will locate on the body of the shuttle, and then when another antenna will institute and another side of his, we call this is bridge. Okay, another side of the bridge. So this shuttle will launch to the space and start his work. He will overturn like here. He will extend his baseline, and this baseline is his arm, or call his bridge. It's the fix, and both sides have the antenna, and this shuttle will transmit the wave to the ground, and the ground will reflect this radar wave, and both sides of the antenna will receive the wave, and he will continue to follow with the Earth's orbit, so he will get almost whole Earth's DEM's information. It just use he will stable baseline, and they almost get the received wave at the same situation. The situation means almost the same atmospheric environment, and almost in the same look angles. So everybody just fix. So let's can get more precise the DEM's result. Yeah, just it is the SAR interferometry's application. But we still want to know how does InSAR work. Here is the shuttle, but right now we almost will use not the shuttle. We need to use the satellite, and the satellite will follow with his orbit, and right now it's from the north to the south, and every 12 days visit Taiwan for the Sentinel-1 satellite. So here we can follow this image. When the Sentinel-1 fly across the Taiwan, they will get the first accuracy SAR image, like the yellow card. And 12 days after, he will get another SAR image. If we got these two satellite images and then make this together, we call this correlation. And then we can get the interferometry. It's like a preview I say, but right now it's work from the satellite. So they are very interesting. It's about if the satellite continue to visit the same place again and again, then we can get the multi-temporal SAR image. And that will can help us do more like time series. But today we just focus on the like the serious or huge events like the earthquake. So you got the earthquake before and after SAR image. You can use this both image to measure how the surface deformation. But when we got this SAR image, we must to know if satellite just pass away from Taiwan, I pick up the face image. It's including the information will tell us how far or how many wavelengths. Actually, it's not, because if we use the 5.6 centimeter wavelength to measure the distance, it will including 30 million more wavelengths signal in the one pixel. Least for the satellites, it is could not loading this data, and actually the phase data we just need the last like the phase, less the wavelength the signals. So if we sync this fringe, use this like the star point, this is not change it here. So when he from the red, blue, light blue, yellow, red to here, this is a wall fringe. We say the color bar is called 1 cycles. It's 1 cycle, it means 2.8 centimeter or 28 millimeters displacement in the line of sight, in the range duration. So we will count to the next is here. Here is the second fringe, and that is third, fourth, 5, and so on. Here is the 10, and the continue count is here is 20. So at least from the 20 to the 0 point for a start point, it has already 567 millimeter displacement. And then you will found if we more close the epicenters, the fringe density is higher than outside or the far away side of the epicenters. This calls the deformation gradient. If the density is very, very high, it means its deformation gradient is very huge, and it make more strong surface deformation or some hazards in this area. So the scientists want to know actually how many displacements, so they will put this fringe to unwrap. It is like a wrap. Every 2.8 centimeter, we will wrap become a fringe, wrap to become a fringe, and so on. So right now we will unwrap this fringe. So we will become like the right sides, become the real line of sight displacements. Okay. So from the A to A plus profile, you found the far away from the fault or the epicenters, the surface deformation will not drop very quickly. But when he very, very close to the epicenter, you have found this behavior is from the linear become curve behaviors. And the other side is for and the other side from the A plus to the epicenters is show almost the same behavior. So you can here you must mention this from the fault, both sides, they are quite different behavior because this fault is lateral behaviors. So the both sides shows different move vector. So the result will describe tell you the line of sight is one is increase and the one is minus. This means the northern part for the satellite is away, and then the southern part of the fault to the radar is increase. So this is right side lateral movement of this image. So this part will away from the line of sight, so it's increase its distance, and then this part will close to the satellite. So this line of sight displacement is decreased. So these areas of it is moved to the right. These areas surface deformation is moved to the left. So both of side of this fault here is go to the right, here is go to the left. We will call it right lateral fault movement. Yeah, it's active fault in the Turkey. And then we can use this information quickly know more information about this earthquake. That's why in recent years, radar satellite become a powerful tool to monitor the earthquake events. And almost every earthquake events, we will immediately to process radar image. Okay, so right now we have some idea about the interferometry. SAR interferometry can useful to measurement the surface deformation. But in the section 2, I try to talk about every stage of the processing. Here he have 4 stages. One is the pre-process, and the second is co-registration. Third is topography phase, and the fourth is make the filter and filter the interferometry. Okay, the first is pre-processing. Right now, I believe like the Sentinel-1, if you have any experience to process this image, you will find this image is more like this, like this amplitude image. It's just the gray colors, and like the in the lake area is more dark, but in some maybe like city areas it will very bright, and in the mountain area is maybe between these 2 colors. Okay, so that is already become the SLC image we call the single look complex image. But actually, when the radar signal go back to the antennas, the raw data should be like this. A lot of echo signal. It's not easy to analysis his phase and surface deformation. So the raw data should be compressed in the range duration and the azimuth duration, become the SLC complex format. And but right now, new satellite image almost supports Earth's SLC image format, but the previews like the ERS or MVC, even ALOS data, they will provide the raw image data. So we need to do the pre-processing, is make it from the raw data become the SLC data. So it's pre-processing. But right now, maybe if you use a recent satellite, you can skip this step. Yeah. But the second is, I think, is the process of SAR interferometry is the most issue about this process. In the co-registration, they included 4 steps. First is precise orbit and the DEM, and the second is cross correlation. Third is feed the 2D offset data, and the fourth is resample. So the first is precise orbits and the DEM. When the satellite flies in the space, we must hope it's always at the same place, keep the same attitudes, and look the Earth, and can get the quite good radar signal. But actually, in the real world, the satellite will sometimes close the Earth or sometimes away from Earth. So he will keep a roughly orbit, but we still need the precise orbit to measure how far he difference between the last time he gets the same information's location. And then it will help us to know his distance between these 2 satellites, use the baseline to get the distance. And another is we need to use the DEM to help us to make this orbit information and the satellite's attitude relative to the surface, how it's changed, or how is the rotation's behavior. So we need this both information to help us to know actually the satellite's we say the attitude is becoming his flight, look angle, and his rotation, and so on information. So here is we'll show you the example is when the first image got the precise orbit, so he can get the quite good look angles and to know how far the surface deformation, the DENs, and have the look angles exchange about this between the geometry about the satellite and the ground. So we can get the perpendicular baseline or parallel baseline, and we will divergence orbit because the image will rotations, and the other orthogonal baseline is like the perpendicular baseline. Yeah. But then next time is, yeah, the image 2 almost the same place, but have a little bit difference between the first times. So the distance we call the perpendicular baseline, but we need the precise orbit and the DEN to help us to get these informations, and we will know they use the different look angle to look the surface. So we need to change this shift or so on based on the precise orbit and the DEN. When we fix them almost look like at the same place and the same look angle and the same orientation, then we need to do the next step is the cross correlation and the fit 2D offset. This idea is when we already use the precise orbit and the DEN data to make them look like the same location in the space, but actually they got the information with some shift or some mismatch. It's not can use the data directly. So first is we want to know this both data how mismatch. How mismatch is in the range direction. The second image should be shift how many pixels, or in the azimuth direction, the second image should be shift how many pixels, and make these two images look like almost the same. So in the figure you will find the first image is like here, is red color, and then the second later image is the green colors. They have some like the shift behavior between these two images. So we want to make sure they are get together. But how to get they are look like the same? We will use some surface characteristic signal, like they have a good buildings, so the reflex signal is very good, and we must make these two signal get together at the same pixel, and it's most like the ground control point. Yeah, we use this to make their can be the right place in the two image, and use this is the very huge or very strong signals location. And then we will found there are some fit, so we will get together and like shift some pixels, make it almost the same, and we will found some area like here is both of them coverage, and we will do the resample. It means for the Sentinel ones, we know their resolution is between azimuth is 20 meters and the range direction is 5 meters. But actually, their correlation, they have some problem is about preview assays. So when they're resampling, they will use the same pixel size to make every pixel become the original pixel size, and to recount this signal, like the average signal, and it becomes a regrading file. So to do this correlation, we can actually trust the two image has already co-registration wheel, and every pixel is relative to the origin pixels. Of course, here we'll include some errors, but it is needed to be discussed. Yeah. And the third part,
Dr. Lu,
yes,
they have a question in the post.
Yeah. Yes.
在那个讯息栏有一个问题。
Oh, okay, sorry. I will check the question. Sorry, I will check. Okay. Here, send the image be processed similar for whatever. Okay. Okay. A sending image and a descending image, they cannot do together because their look angle is quite different. So you have found like the mountain area or some topography characteristic like the buildings. You look the ascending image, ascending look angle and the descending look angle, they are quite different because the reflex signal is totally different. So even you do the co-registrations, you actually knows the sense pixels didn't reflect the same signal. They are totally different signal for different look angles. So we always ascending image process with ascending image, and the descending image process with descending image, and then we can fix their almost like a sense radar path, like the same situations and the same look angles, and they focus on the same service targets, so that the signal can be processed. But if you use different angle, the data should be like almost the different thing. Yeah. So I hope this will answer your question. And the second is the produces good information. What is the idea of itself? Okay. Okay, I will tell you is the question. Explain this question later. But right now I can tell you as less as you possible the baseline. Previous, if you use the like ERS, we earlier we use these satellites. Sometimes the baseline could be like 800 meters. It's quite large. For us, some elevations we call the DEM errors we are including in your interferometry. So we want to use less than 200 meters baseline and to make one image pair. But right now, if you use the Sentinel-1 satellite, the idea is control the baselines is less than 100 meters. So I believe if you use the Sentinel-1 image, the baseline is almost not a big problem for you. But in the previous SAR satellite data, you may consider this issue. Yeah. So I just answer these two questions. So I follow this, and if anyone have a problem, you can just leave your message. Okay. So I keep going. So when we already well done the co-registrations, the next step is we need to measure in the topography phase. Topography phase is due to the when the radar signal to the surface, they will reflect the signal back to our antenna. So when it reflects to our antennas, it will help us to know two different radar look signal. Its reflex signal is quite different. It's a little bit different. I can actually say it's a little bit different. So we need to know this both sides, these different sides look at the same topography. They have some different look angle. So this topography will cause some shift or some error, including in your interferometry. So we need to calculate this. So we need to know the both sides of the look angle, and we know the satellite's behavior, and to calculate the topography effect. So actually, in the satellites, this is the radar image. It's already project to the longitudinal and the latitudinal system. It's like Taiwan Island. But actually, when you use the radar, the SLC radar image, you just display this intensity information. You have found the radar look like this. The Taiwan Islands look like this. It's not you image. Outside is the north, outside is south. Yeah, and the Taiwan become shorter and fatter because it's right look angle. So we need to put this information back to the satellite, tell satellite how the topography affect to your look angles. So that will help us to remove the topography effect. And the third is make and filter the interferometry. When we already do the topography phase, we can reduce the topography phase, and the some is like Earth, the curve, and some orbit issue. We will make the interferometry. But in the sometimes like the earthquake events, you will find a problem is here is no data, or some outside where no data. This is because here is quite a bad coherence. So we will lens is empty, and the lens we will use filters to make it fill some information here, or when some place will like some error signal to make the fringe not very good, we will use the filter to do. But how many filter or how intensity of the filter is need to discuss, because it depends on your original interferometry. But if we can do its quite good filters for your interferometry, it will help you to unwrap the interferometry better. But if you don't use the filters, it will make you unwrap difficult. So sometimes it will do a lot of try and error to find the best situation for like the earthquake events. So when you finish these four steps, and then you consider a lot of situation about these two images, you can get the we call the SAR interferometry, but sometimes we will call it the differential SAR interferometry. Some people maybe heard is InSAR. It means we got this information from here. Okay, wait a minute. I saw.
Also, yeah, another question in the audience.
Yeah. I saw. Okay, we identify that kind of formation cause the earthquake. Yes, we can do that. So like the previous I can go back. Turkey earthquake. Yeah, here. Okay. Here's you can use the fringe, the path that goes through the path. This path goes through is tell you the signal is away from the satellite, and here show you the fringe increase is means like toward to the satellite. So we will know this part of the surface is away from the satellite. Here is moved toward the satellite. So you know here is away, here is toward. So we know this fault, along this fault, northern side is to move the right side or subsidence, and the southern side is move the left side or uplift. But in this case, in the Turkey, in the Lismi earthquake, we know this fault behavior is a lateral fault. So we know it's the right lateral, and this earthquake behavior is matched with our previous geologic data. So this is tell us the same move right lateral behavior. Yes. And okay, my question is that there is target some structure like ocean wave car tree. Okay, about the ocean wave car trees then and affect the image resolutions. Okay, actually we can do that. It depends on the radar's resolution. Like if you want to get the ocean wave or like the car, you need quite good high resolution. Maybe the resolution should be increased to 1 meter, or some case 50 centimeters. So it depends on the radar's resolution. So it could be to tracing a target. Actually, a lot of application in the ocean is they want to tracing the ship like their durations or how many ships in the oceans, because in the ocean the ship the reflection signal is quite good. So I think it could be do that, and it have a lot of application. Yes. So I believe this question is okay. And will they affect radar image? Yes, yes. Okay. So I'll keep going. So here, yeah. So when we when we remove like this topography event, error or some Earth curvatures or some orbit errors, so we can get the InSAR, we call the differential SAR interferometry. It's especially to say we remove the topography event. So we actually measurement is the displacement, not including the surface. We not including the elevation. We just measurement the surface deformation. So let maybe from a few centimeter to few meters movements. So we can summarize all the effect in the phase. It may including Earth curvature, topography phase, surface deformation, real surface deformation, and the orbit error, and the ionospheric delays, tropospheric delay, and the phase noise. How this information is between the satellite from the space to the surface. It will include a lot of information in this path. And the right side corner is show the topography phase effect and the Earth curvatures like here. But we can summarize this effect like here is because ionospheric delay and tropospheric delays like the atmospheric delay. So there are 5 components in the interferometry. First is real surface deformation. Second is atmospheric effect component. And the third is orbit error or orbit shift component. And the third is topography. This topography effect, including the topography phase and the Earth curvatures. And the last is noise. So until the session 2, I think is no questions. I will continue to next sessions. Okay. When we already got the interferometry phase, okay, we will mention there are 5 components, including this. So actually, for me, we really want to know is real surface deformation. But some people maybe want to know the atmospheric or others component. But for me, we want to know the surface deformation. So others components for me is not the most important thing. I want to remove them. So the first important for the geodesy, use the radar image. The atmospheric effect right now is the big issue, or is the most important issue that we want to solve it. Just I mentioned before, it's including ionospheric and the tropospheric effect. And first we will talk the tropospheric effect. And in the tropospheric, they have 2 kind of the delay. One kind is the wet delay, and other is dry delay. It's relate with the wet condition, yeah. And the right side is about dry delay. It will follow with the topography. It means when the topography is when the elevation is higher, the wet delay should be occurred in these areas, yeah. And so it's have like almost a curve between linear behavior about both style of the physics. And the right side is the another we call the wet delay. You will find the wet delay is very crazy. It's sometimes it will come here, sometimes it will come here. It's just like a random behavior exists in we said in the tropospheric layers. So previous study, they have used some like experience functions or GPS or many idea to reduce or to remove this signal. But here is still need to some observation data to help us to know that. So here have some examples. In the 1995 ESF, the ERS-1 and the ERS-2 radar satellite radar image, they built the behavior is they want to make ERS-1 and the ERS-2 just have a 1 day difference to monitor the same location. So left side is ERS-1, B is the ERS-2. They compare to the same master image. You will find just 1 day's difference, but a lot of fringe occurred. If here didn't have any earthquake or anything, here just very peace. But in the 1 days, there occur a lot of fringe, so it must be come from the atmospheric. And you can find this, the right side is the elevations. Here is mountain areas. You can see from the plane to the mountain area here, like 1, 2, almost 3 fringe. And then the southern part here is the mountain area. You have found here, like this shape is very close to the topography. So we know the atmospheric, if the dry delays, it will follow with the elevations. But it still have another big crazy things is like turbulent tropospheric effect. Here is like June to July is in the Greece, yeah, and they just 1 month, and here shows over 3 fringes in the C-band satellites. It means almost 8 to 10 meters displacement. I think it should be very, very serious land subsidence, or maybe like very, very extremes, like maybe volcanoes or tremors active, they will cause like this. But actually here is nothing happened. And here is close relay with the strong raining. The behavior is sometimes will show in Taiwan, or maybe I think in the hard areas maybe face these problems. Just like when in the summer afternoons, you always will find the cloud will accumulate very quickly, and then maybe 30 meters ago, after you have a lot of strong rainfall at maybe 1 hour, and the lens, the clouds is disappear, the sky become very clear, and it's just like nothing happened. But if at these times the radar satellite just passed away and receive the radar signal, they will infect by these behaviors. So it will make like this, like we call the turbulent tropospheric effect. Another we call it is about the ionospheric effect. Right side is example in Taiwan. In the 2006, Southwest Taiwan have a serious earthquake. Is the main known earthquake. And when this earthquake occurred, we still use the Sentinel-1 image to do the SAR interferometry. And we want to know the surface deformation. And the left side here is first we got this result. Yes, we found the earthquake at here. The epicenter is here, and that caused the surface deformation. However, if we notice from here to here, it caused 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is almost 25 centimeters displacements. But at that time, only here have deformation. From the 1000 to the middle of Taiwan, it didn't happen anything like this. So we found some data. We know at least earthquake effect, Taiwan faced a serious ionospheric density change. So it will cause the ionospheric effect in the Taiwan. So we use some method to remove this behavior, and then we'll get the real surface deformation about the main earthquake. Yeah, so this case will show you the atmospheric. It's not always exists, or he always exists, but not affect the radar image a lot or less. It's sometimes like the randoms, but right now we want to make it estimate this is the error, like continue to calculate. So scientists will provide some method to deal with the atmospheric effect. First is ignore. Okay, just like a preview I said, in the main earthquake, first we ignore this part. We just focus on a very serious surface deformation. But when we finish a lot of work, we go back to think about this ionospheric should be removed. But at the big event like earthquake, actually the signal is very strong, stronger than ionospheric or stronger than the atmospheric effect. So we will ignore them first. So this just for some huge events. And the second is quantify. Quantify means they will measurement real observation data that they can to calculate this real effect about the radar's signal processing. And the third is model based on other observation. It means like the GPS or other satellite data to make it to reflect. But it have some problems. Sometimes you use others observation, your other satellite data. They are not at the same time, but they can give you areas distribution or like an area pattern. I think it's quite useful. And for this increase SNR by staking of time series, yes, it's sometimes if we want remove atmospheric effect in earthquake, we will use not only before and after this image. We will use before 2 and after 1 image, or before 1 and after 2 image. And we use cross a lot of image to staking them together and make a mean displacement. And then that will help us to reduce the atmospheric effect, because this event will not exist every pair. It may be just exist some pairs, but we use static method to reduce the direct effect. And then the fifth is the model based on the relationship with topography, just as I said previous the dry delay. And then sometimes based on the model, it's like the weather model is some in the European, they have already used this to try to reduce this atmospheric effect. So right now, this is the most important issue for our interferometry processing. Okay, the second part is the second component is the orbit. Actually, the orbit should be the every ray point in the left figure will show you they catch the radar signal, the location. So you will find a difference baseline between these 4 ray points. Because they have different look angles, so the baseline will cause some look angle problem. But actually, orbit problem is previous satellite have this problem. Right now, satellite will the scientists and some satellite engineering they already reduce this error almost zero. I cannot say almost skip this error, but still remain very tiny effect in our interferometry. Just like the Sentinel-1, they just can make the baseline less than 100 meters, and their orbit, flight orbit, precise orbit can precise to the few centimeters accuracy. So the orbit effect in right now is almost solve these problems. And the next component is topography. Topography you should need to think about the topography is the 3 dimensions informations. So it will contribute in the topography phase, or here say topography fringes. So different look angles, the topography will feedback different topography fringe. So we want to make this effect to more or less. So first is we support quite good resolution about the DEM. It means if your DEM is very good and very well, so I believe the topography effect will reduce. Another problem is about the baseline effects. It will caused by they separate. But if we, for examples, we use the ARS and the MVC bands satellite, their incidence angle is 23 degrees. Use these equations, you can find almost the baseline 1000 to divided by the baseline is the elevations effect. What it means? It means if the baseline just 20 meters separate, every 500 elevation can increase you 1 feet. It means have a 2.8 centimeters errors. But if you use 100 meters baseline, like every 100 elevations change will cost you 1 fringe. So that's why we saw if in the earthquake events like this, topography error is not to be mentioned, and everybody will focus on the more is surface deformation. Another here is the 100 baseline is will another is displays why the Sentinel-1 satellite can do the time series monitoring, because he's if he always keep the 100 meters baseline separation, the every 100 meters will create 1 inch. If we want to monitor the area, is like the length of subsidence. It's very slowly, but the elevation most in less in 50 meters, because almost the length of subsidence area is occur in the plan. Here I say the length of subsidence is due to the groundwater pumping, so it's most like the coast areas plan. So the elevation is very low, so like this component almost cannot affect your observation areas. Okay, and the last one is about the noise. Noise has two components. First is from the ground surface change, and make the coherence is value very low, so it will cause the noise. Another is the system or thermal noise is from the satellite base is machine. The first ground surface change and cause the noise. It sometimes happen in the earthquake, especially in the fault line. So some case in the big earthquake, we want analysis fault lines phase displacement information, because the low coherence will make our unwrapping errors. And here the coherence, we can use the optical satellite image and the coherence image to make some comparison. In the forest areas, you have found the coherence image is quite low. Wait a minute, I found a new question. Handle atmospheric, or we do this so okay. For my knowledge, you just process in a step. You cannot remove atmospheric correction in a step, this software, but you can output your result and use other like the GPS develops the atmospheric information, or you can use weather model derived by the atmospheric effect. You can use this information to correct your original SAR results. And yeah, so we do this correction during the process. Put into InSAR. Snap results won't any correct, just including like the topography, orbits, and like the Earth's curvations, like this component, it will correct in Snap. But if you want to correct like the atmospheric effect, you need output the data from Snap and use other data to correct it. I hope this will answer your question. Okay, I will continue to the next component about the noise. And the biggest source about the noise is is the ground surface change, and then the ground surface change will occur. Yes. Professor Lin says correct. Yeah, and the ground surface change actually we have found here is the two image pair across the coherence results. In the mountain area, you have found the coherence is very low. The dark color means the coherence near zero, and the bright color means they are almost the same. But in the city areas, you have found the coherence is very high. And another interesting is about the river here. You found the coherence is quite good enough because in Taiwan, the river only very small areas have the water go past. This very, if not the rainy season. Other side is full of the rock or centimeters components. So the ground surface cross is very high, so it could become a good reflect signal to the radar to reflect the radar signal. So this part will become a good coherence, if not the big raining or any like the flood event, yeah, like here. So when an earthquake occurred, some place the coherence will drop like the forest, so it's hard to us to get this information. So therefore, in some areas we must focus on the coherence value, like the mountain area. Yeah, this is when we process the unrapid behavior of this interferometry. This area you need very careful because the coherence very low, so you may not so confident that this image or this signal is quite good or make us to get the real surface information. So the noise should be considered, but it's not like trouble like the atmospheric. It's because we have a optical image, so it can help us to know which part is more reliable, which part is less reliable. Yeah. So in the incoherence areas, the unrapid error will occur. So this is the noise that we need to focus or to care for. Okay, and the last part is here. I just mentioned some software that you can process radar image until to the interferometry SAR or we call the InSAR process. And the free software is step you will learn next week, and by the Dr. Nina, or is expert about process this software. And the other is ICE, is from the NASA and the JPL. And the third is the GMT SAR from the UC San Diego. And some commercial software like Gamma, MV, SARscape, ERDAS, Diapason, can do the good result for you. And last is in the right now satellite and the preview satellite. Maybe you have already read these pictures. And we already apply a lot of image like the Sentinel. But I believe if you want to do the all event or like time series analysis, you can use some all C-band satellite like the ARS and VSA. And right now is another L-band is we're waiting for the InSARs. And actually here is we can say is famous. A lot of commercials minor or we can mini SAR satellite already launched in the space, like ICE is from Sweden. If I not wrong, yeah. And other is like the Capella, yeah. So I think a lot of satellite that you can use this. So the last step is here, just we can know the golden age of space born star is coming. So I believe everybody can do a lot of interesting things in this area. Thank you, everybody.
Thank you, Dr. Lu. Also have questions.
Yeah. I know. I want to ask a ground surface change if we want to get elevation change on chromite in the chromite. Okay. Actually, you want okay. I answer the Connie first. Okay. You want about the core mining is the core mining surface deformation. Maybe sometimes we will use the time series surface deformation. Maybe use the high resolution like the TerraSAR or Cosmos Sky satellite. Their resolution from the 1 meter to 3 meters, and it will focus on the core mining's behavior, like some a little bit some part like the landslide behavior, some part like subsidence behavior. Maybe it's good for monitoring. And should we always use it as image for correlation? Another is I reply the Dana. Okay, Dana. The always use SLC image for correlation. Right now, most software will use the SLC image to correlation is because, like the Sentinel-1 image, you just download this image is the SLC format. If you want raw data, you need spatial to apply to lens. And at that time, you maybe have the chance to use the raw data to do the correlation. But I think it's not easy to do because the signal is very sparse, so not a concentration. So it's not easy to make the right component to every pixels and make them get together. So I think SLC data is quite good situation or quite good option for us to make the correlations. And it is possible to persist rate numbers over different levels. just I say you have the, you can try to do co-registration from a level 1.0, but I think it's not easy to do that. Yeah, because the signal is to noise, not like the SLC quite good. So I think maybe you can use the SLC level 1.1 this level, and to do geocoding become the 1.5. Actually, in the Sentinel-1, the SLC data, the resolution is from the azimuth is 30 meter to almost 3.5 meter in the range. And but if you found the InSAR, they not only provide the SLC data, they will provide a GRDH data. This data, the resolution is 10 meter and 10 meter in the range and the azimuth. But that's already processed. But they just provide you amplitude information. And in the SLC image, you have two kind of information in your image. Is the amplitude, is the intensity image and the phase image. So you can do this, become the geocoding result. It's okay. And if you got the raw data, you still can do this to become the geocoding. But I never use the raw data directly become the geocoding. I just use the raw data become the SLC data, and then use the geocoding become the like the level 1.5 image. Okay, this is the answer for Dana. And the next, okay, this is Aguk. I hope I pronounce it correct. Oh, I hope. If wrong, I'm sorry. But your question is about the PS inside the spots. Yeah, yes, it's quite different to different Matthew. I'm not sure other teacher will talk about this, but in my next talk is about length subsidence. I will discuss about PS inside the spots, because the boss Matthew is try to monitor slowly surface deformation. So it's used different kind of the main idea. One is have the only one master image is for the PS, and for the spots you can use a lot of image pair, but you didn't have the same master image. It's the main difference idea between these two techniques. So you mean when you place have very complicated, including urban area, vegetation, and maybe like the bare land areas. I know which one is better. PS inside is good or spots is good. Actually, right now the most advanced process is combine both data. It means they will do the PS in this area. They will do the spots in this area, and then they combine these two results and get together. So that I think you don't worry about your area is urban or your area is vegetations. They will solve all the problem when they get together. Yeah. I hope I already finished your question. Aku.
Okay, thank you, Dr. Lu. And today is the Taiwan National Day. It's a day off, so I'm really grateful for Dr. Lu's assistant, and also the Meng's the teaching assistant as well, and also the attendings of the audience. Then is the end of the lecture. Actually, as mentioned by Dr. Wu, Dr. Wu also have another talk about the subsidence, right? The topic.
Yes, let's subsidence. Yeah.
Subsidence. And I remember we also have the short quiz. So now the monitor to move to the short quiz.
Oh, okay, okay. It's Nina. Oh, okay.
Nina.
Hello.
Nina.
Hello. Sorry, just a quick announcement. So because we're going to have this hand-on exercise next week, and I realized I forgot to mention in the slide that please remember to use a mouse. Okay. I know it sounds funny to make this announcement, but I know many people, they feel pretty comfortable using the touchpad. But then you will realize it will be a bit difficult if you use touchpads next week. Okay, so that's it. Thank you.